Hi, why the fanfare? It took me quite a while to find the code to get this Arduino Nano ArduCAM SD card set up to work and store a properly formatted JPEG photo. In the background, you can see the picture of the Rubik's Cube that was displayed in Apple Preview. Follow the URL that you see on the screen to find the Arduino source code, as well as links to where you can purchase all the components used in the build. This build is a prototype for the Sacramento L5 Society Balloon Device Project. We're planning to fly this camera as well as other Arduino instrumentation on a balloon that will ascend to over 100,000 feet above the Earth's surface. Let's take a closer look at the components that comprise this device. We have the Arduino Nano controller, which is in a breadboard under all those wires. It's connected to an Apple Mac Studio via USB cables. Then there's the ArduCAM in the same breadboard behind the Nano. And we also see a second breadboard into which is plugged an SD card. That's where the photo from the ArduCAM will be stored, and that will allow transfer of the SD card to the Mac Studio card reader. To load and run code on an Arduino Nano, use the Arduino IDE application. Here, we're opening the application to see the code that we've written. If you're new to Arduino, get a starter kit that will have instructions as to how to get and load an IDE, as well as many working examples. After the IDE opens, you can plug in the serial cable from your Arduino Nano, and it will begin to run the code. The code is finished running. Let's take a moment to see what it did. The code first checks to see if it can initialize the SD card. That means the SD card is plugged in and functioning properly. Capturing means the Arduino code has sent the instruction to the camera to capture a picture. Capture done means the camera has returned control to the Arduino code. Found FFD9 means that the Arduino code has detected the proper ending to a JPEG file. JPEG saved means that the Arduino code has sent the bitstream returned from the camera to the SD card. Now it's time to transfer the SD card from the device assembly to a Macintosh USB serial port. The SD card reader connects to the Mac via a USB-C serial port. The SD card then mounts on the Mac desktop like a little disk drive. Double-clicking opens disk drive folders and shows you the files on the drive. As I mentioned, it took quite a few attempts to get this right. The files with the dark icons to the left are properly formatted JPEG files. Those that were white are improper and will not open in Mac Preview. Double-click to open the file. And here's what we were trying to do. Get a file from the Arduino camera and display it on the Macintosh. For proper disk drive handling, close the folder and eject the drive. I haven't seen the SD card damaged if you just pull it out of the socket reader, but it's best to eject it properly. Yikes! Here's the wiring diagram for the assembly. Don't worry, it's not as bad as it looks. Let's zoom in on the nano board itself. Electricity in circuits flows from the power pins to the ground. There are two types of input and output pins: analog and digital. Analog would deal with continuous changes in voltage, like from a thermometer or a light meter. Digital inputs deal with on-off, high-low signals, as if from a switch or to tell a device to begin functioning. The pins labeled in gray allow the microprocessor on the Nano to communicate with the microprocessors on the connected devices. Now, let's look at the table that tells you how to connect the wires. Yikes! Don't worry, this isn't as bad as it looks either. Okay, so here's the schematic of the circuit that you want to build. Now we'll look at the actual physical components that you'll use in the build. Notice that except for the chip select, all the pins are the same and that they're labeled on each device. Here's two little breadboards holding the Nano, the camera, and the SD card module with the SD card inserted. You can simplify your arrangement of the wiring by, as the physicists say, breaking an impossible problem into two difficult ones. Here's a schematic of an earlier build that I did. This is the kind of schematic you'll see all throughout the Arduino starter kits. This build used a Solo Nano on an even smaller breadboard. It also used the ribbon cable that came with the camera. The ribbon cable consists of 8 pins all stuck together, which conveniently connect to all the pins on the camera. You can then insert the pins into the breadboard to connect to the corresponding Arduino Nano pins. Now, when we look at the pinout table, it's not as hard to understand. A note about the Arduino Nano power supply pin. The Nano is supplying power to the camera, but where does the Nano get its power? The Nano gets its power from the USB cable, which makes it very easy to prototype. Arduino Mega and Uno kits also come with a battery that will allow you to power your build independent of the USB cable. Here I've placed the Nano and the camera on a single breadboard and used individual wires instead of the ribbon cable. Now, look at the color of the wires connecting the camera and then use the same color wires to connect the SD card module. All the colors from both the SD card module and the camera connect to the same Nano pins except for the white wire. The white chip select wire from the camera connects to Nano pin 10, and the white chip select wire from the SD card module connects to Nano pin 8. With the components wired, we can now take a closer look at the code. Notice that the chip select pins are defined in lines 9 and 10. As the code scrolls, you'll see the serial print line commands print messages to the serial monitor. If the code finds the serial card, it'll print SD card initialized. Otherwise, it'll print SD card failed, usually because you forgot to plug it in. Then the code runs the command mycam start capture and prints capturing. The code waits while mycam get bit is true. When it's false, the camera returns control to the code and the code prints capture done. Now the code opens an incrementally numbered file name on the SD card, does some preliminary checks on the bit stream to see that it's proper image. The code then begins to write the bit stream to a new file so it can check that it has proper JPEG content and only JPEG content. While it's writing, it looks for the hex characters FFD9. FFD9 indicates the end of the JPEG image bitstream. And this is important because it turns out that the camera transmits noise after it finishes transmitting the JPEG image. If this noise ends up in the JPEG file, JPEG readers won't be able to display the image. Finding the FFD9, the code stops writing to the check file and knows it can now write that file to the SD card. After the write to the SD card, the code will print JPEG saved to the serial monitor. One more thing. At the end of the code, you'll see there's a loop with nothing in it. That's because the purpose of this build was to take one properly formatted JPEG picture. Future builds will take a picture after a button press, take multiple pictures at set time intervals, or even after a detected change in a parameter like temperature, altitude, or cosmic ray density. And there you have it, an Arduino component build and Arduino code that will take a properly formatted JPEG picture that you can display on your microcomputer. You can find more details about this build on the Sacramento L5 Society.nss.org website. The link displayed will take you right to the details of this build, and from there you can download the Arduino code. Now for some practical advice as to how to build your own custom devices in Arduino. First, get yourself an Arduino starter kit. An example is Elegoo's Mega R2 Project Kit and the Uno Project Superstarter. They cost about $60 and $40 a piece, and they're available on Amazon. And they are excellent, meaning that they work. They contain links which will allow you to download the Arduino IDE and sample code. The IDE actually has sample code within it, so you can load one of your first programs immediately. The PDF with the kit instructions contains over 20 examples detailed with code, and all the code is provided. The examples are amazing. Photocells, stepper motors, relays, controlling stepper motors with remote ultrasonic sensors, joystick modules, digital inputs, active buzzers, tilt ball switch, 7-segment display outputs, and even an IR receiver module that would allow you to receive infrared signals from your TV remote. The kit instructions even contain simple introductions to coding and basic electronics. Building the examples allows you to get familiar with the wiring techniques, get the technique of inserting the wires, identifying the pins. You can also change the code a bit, adding print line statements and other minor changes. All the code has been written for you, and again, it works. So I ran Blink, which blinks a light on the Arduino controller, downloaded and ran the LED matrix controller, displayed 8-segment characters on the 4-digit display, connected a thermistor and watched the temperature rise on the display when I grabbed it between my fingers. So I got familiar with wiring the boards, downloading the code, and watching different code do different functions. But the kit doesn't come with a camera. So I bought the AutoCAM for $25, and there's the respect that makes calamity of so long life. The instructions for the camera had a website where I thought I'd be able to download code. And indeed, there was code on the site. But as I downloaded it, it seemed to work by taking a picture on the camera. But I hadn't yet tried to put the camera picture onto an SD card. So I asked ChatGPT for an AutoCAM program that would take the picture and put it onto an SD card. And I did get a program that took a picture and ran the bitstream to the SD card. However, when I put the SD card into the Mac and it opened as a folder, it produced those files you may remember with the little white icon to the left. Those files are not proper JPEG files that Preview can open. What followed was interactions with ChatGPT multiple times for a few weeks. What's wrong with the JPEG file? How do I fix the JPEG file? In the process, I learned all about the internals of a JPEG file, which I didn't mind, but it wasn't bringing me to the goal of creating a picture that I could read on the Mac. Finally, I prompted ChatGPT, none of this is working. Let's start over. And then ChatGPT did it. It produced the code that I've shown you in this video. I had also scoured the web on my own, finding large masses of Git repos and all sorts of files that claimed to run an ArduCAM, but they didn't work. So the code I provide, if you go to the SAC-L5 website, might be the only code on the internet that will run an ArduCAM and produce a Mac-compatible file on an SD card. A bold claim, I know, but go find my contact information on the SAC-L5 website and let me know if you have another working ArduCAM Arduino code file. But please don't say it's over there. Why didn't you do this? I did it like this. You need to provide the actual file. I may just have had really bad luck in trying to find that file, but I wanted to tell you because if you do want to build a device, Arduino, of your own design with your own code, your experience will probably be something like what I just described. And for any non-engineers watching this video, what I've just described is essentially what engineers do. There's a pile of stuff over there, and it's not doing what I want. So I'm going to look at it and play with it until it works. Thank you for listening, and I hope it's been interesting, and I hope you do buy one of those Arduino kits because they're really fun. And please visit the Sacramento L5Society.nss.org website because not only is the Arduino code over there and more explanations, but there's also a lot of other fun stuff there too.